Hi, I'm Ellie Pinches, an Education Officer here at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our Weather and Climate Teaching Guide with accompanying classroom resources which can be found on our website, MetLink. There's links in the text below. In this film, I'll be focusing on tropical cyclones. Of all the weather systems on Earth, tropical cyclones produce some of the most intense and damaging weather. Tropical cyclones are known by different names in different places. Hurricanes in the Atlantic and the Northeast Pacific, typhoons in the West Pacific, and cyclones in the Indian Ocean. Tropical cyclones are storm systems that often make the news when they make landfall in populated areas, and sometimes cause widespread devastation to homes, infrastructure and crops. The largest losses of human life due to weather events are also associated with these systems, with death tolls sometimes in the hundreds and even thousands. Usually the majority of deaths occur in the aftermath, as flooding and damage to the local infrastructure lead to disease, drowning and lack of clean water supply. The image here shows a satellite image of Hurricane Katrina, which hit the Gulf Coast of the USA near New Orleans in August 2005. This storm led to an estimated 1,800 deaths, mostly through disease and dehydration in the days following the storm. Whilst intense storms are very common throughout the tropics, tropical cyclones need very specific sets of ingredients in order to form. These are 1. Warm ocean temperatures greater than 26 degrees Celsius to a depth of at least 60 metres. Tropical cyclones only form over oceans, never over land, as they need a source of both heat and moisture. Even if the surface waters are very warm, the strong winds in a developing cyclone cause mixing of the surface layer of the ocean, bringing water up from below the surface. If this water is very much colder than the surface water, the supply of heat to the system will be reduced. Number 2. Latitudes greater than 5 degrees north or south of the equator. Cyclones are rotating systems and so only form in regions with sufficient component of the Earth's rotation about the local vertical or a significant Coriolis force, which we went through in Chapter 8. The Coriolis force is 0 on the equator itself and only becomes large enough to generate rotation within a weather system poleward of 5 degrees of latitude. Tropical cyclones, like mid-latitude weather systems, which we looked at in Chapter 17, rotate in an anti-clockwise direction in the northern hemisphere and a clockwise direction in the southern hemisphere. Number 3. No large changes in the wind speed and direction with height, which is known in meteorological terms as low wind shear. Cyclones rely on the development of tall columns of convective cloud which extend about 10 kilometres upwards. If the wind is changing too much with height, these columns of clouds cannot form through a great enough depth of the atmosphere, as the tops will be constantly blown away. 4. Lots of moisture through the depth of the atmosphere. As well as large wind shear, a dry atmosphere can also act to prevent deep columns of cloud forming. And 5. A pre-existing disturbance in the atmosphere. Tropical cyclones do not form spontaneously from nothing. There needs to be an area of enhanced thunderstorm activity which can act as a focus for the development of the cyclone in the presence of all the other conditions listed before. Forecasting the formation of tropical cyclones relies on early identification of these pre-existing disturbances and then recognising which ones will amplify into full-blown cyclones. The development of tropical cyclones is a complex process and is still the subject of much research. In simple terms, a cyclone acts like an engine. It converts the energy available from the warm ocean surface into strong vertical air currents and horizontal wind speeds via the evaporation of warm water from the ocean surface and the subsequent condensation of this water vapour in deep columns of cloud around the centre of the storm. This deep cloud often forms an almost circular ring called an eye wall around the very centre of the storm, which itself is free from cloud. Thankfully, cyclones are rather inefficient engines, converting less than 10% of the available heat energy from condensation in the clouds into the mechanical energy of the motion of the winds. There is an important positive feedback mechanism which allows cyclones to develop into intense systems. As a system starts to form, evaporation from the ocean surface acts as a source of heat and moisture for the formation of deep clouds. As these clouds intensify, strong rising currents of air in the eye wall develop around the storm centre. Near the surface, air is drawn into the centre of the storm to replace the rising air. This inrushing air near the surface results in strong winds which increase the evaporation from the ocean surface. This evaporation provides more heat and moisture to the clouds, making the rising air currents within them stronger and thus intensifying the surface winds even further. As the system develops, the Earth's rotation acts on the inrushing winds, deflecting them into a pattern that rotates about the centre of the storm, spiralling in towards the centre. A result of the mechanism for development described here is that the most severe weather, the heaviest rain and strongest winds, is strongly focused around the centre of the cyclone. In this figure, the diameter of the almost circular region of cloud associated with a tropical cyclone is about 800 kilometres. However, the most damaging winds and heaviest rainfall are concentrated within the innermost 200 kilometres of the storm. The eye of the hurricane is the clear, almost circular area in the centre of the storm. In this area, the air is sinking. As it sinks, the pressure of the sinking air increases because there is more air above it. As the pressure increases, the air warms. As the air warms, the rate of evaporation increases, and so any cloud droplets disappear, leaving the air clear. However, despite the fact that the air is sinking in this area, the surface pressure is low. In fact, the lowest surface pressures are in the centre of the tropical cyclone. This is because the other air motions associated with the tropical cyclone are taking air away from the area. There is less air above the surface. This is a common misconception to look out for. In mid-latitude cyclones or depressions, which we looked at in Chapter 18, we associated rising air with low surface pressure. The physics behind why there is sinking, warming and therefore clearing of the air in the eye wall of a tropical cyclone is still an area of active research. The decay of a tropical cyclone usually occurs when the source of energy from the storm is removed. This source is the warm ocean surface. This may be due to the cyclone moving over land or into an ocean region with lower surface temperatures. An increase in vertical wind shear, so the winds changing at different heights, can also bring about the decay of a tropical cyclone. Remembering that winds blow anti-clockwise around a low-pressure system in the northern hemisphere, then the fastest winds will be on the right side of the storm, where the rotation reinforces the direction the storm is moving in. When a hurricane makes landfall, areas hit by the right front quadrant typically sustain the worst damage. Storm surges occur as a result of the combination of low pressure, as sea levels rise by approximately 1 centimetre when air pressure falls by 1 hectopascal or 1 millibar, and the wind carrying surface waters in the direction of the coast. High tide can also exacerbate the problem. In this figure, you can see the difference in names for tropical cyclones in different basins, which we mentioned at the very start of this video. Be careful when you're using local names, for example a hurricane, if you're looking at global tropical cyclones as a whole. Given the relatively short period of observations of tropical cyclones, it is very difficult to say whether there has been any significant change in the number or strength of tropical cyclones in any of the main regions. The IPCC's 2018 1.5 degrees Celsius report summarised that tropical cyclones are projected to decrease in frequency, but with an increase in the number of very intense cyclones. Heavy precipitation associated with tropical cyclones is projected to be higher at 2 degrees Celsius compared to 1 degree Celsius of global warming. In coastal regions, increases in heavy precipitation associated with tropical cyclones, combined with increased sea levels, may lead to increased flooding. The direct force of wind and waves associated with larger storms, along with changes in storm direction, increases the risk of physical damage to coastal communities and to ecosystems such as mangroves and tropical coral reefs. These changes are associated with increases in maximum wind speed, wave height, and the inundation, although trends in these variables vary from region to region. In some cases, this can lead to increased exposure to related impacts, such as flooding, reduced water quality, and increased sediment runoff. Sea level rise also amplifies the impact of storms and wave action, with robust evidence that storm surges and damage are already penetrating farther inland than a few decades ago, changing conditions for coastal ecosystems and human communities. This is especially true for small islands and low-lying coastal communities, where issues such as storm surges can transform coastal areas. Changes in the frequency of extreme events, such as an increase in the frequency of intense storms, have the potential, along with other factors such as disease, food web changes, and invasive organisms, to overwhelm the capacity for natural and human systems to recover following disturbances. This has recently been seen for key ecosystems such as tropical coral reefs, which have changed from coral-dominated ecosystems to being dominated by other organisms, such as seaweeds, with changes in associated organisms and ecosystem services. There are many useful resources about tropical cyclones, some of which have been included in the text below. We also have an entire scheme of work on tropical cyclones on our website MetLink. This is the last film in this series, so we encourage you to go back and rewatch any videos that you might find helpful. And please do go and explore our weather and climate teaching guide, which can be found on our website MetLink.